Welcome into this week's Degrees of Science. There's been a lot of recent news about an uptick in earthquake activity in parts of West Texas, including a 5.1 magnitude earthquake on July 26 near Snyder. Well, this week we're talking with Dr. Peter Hennings. He's a principal investigator for the Center of Injection and Seismicity Research at the Bureau of Economic Geology at the University of Texas. So, Dr. Hennings, I guess the first thing is, do we know if this uptick in earthquake activity is natural, or is it more induced earthquakes that are taking place?
Good morning, Brady. It's our assumption that these earthquakes are human-caused, and they're related to the other earthquakes that have occurred throughout the Permian Basin region around Midland and Odessa in the last few years. That area near the county line between Scurry and Fisher, it's not known for natural seismicity. The pattern of the earthquakes and the relationship to human causes in the oil field are very similar to what we've seen in many other cases in the Permian Basin region. So we need to do the work and compile the data and let that take us where it takes us. But we can presume, I think confidently, that there is a relationship between oil field activities and this particular cluster of earthquakes, which is quite pronounced.
So how exactly would be oil field activity, how is that impacting and causing earthquakes across Texas?
All right, let me back up a little bit on that. So earthquakes come when you have an existing geologic fault that slips. And geologic faults, of course, do slip over geologic time and make earthquakes. In West Texas, there are many of these geologic faults in the subsurface. They're many millions of years old underneath our feet, down in the ground, maybe 10,000, 15,000 feet underneath us. If the stresses around those faults become unstable, those faults can slip in local areas and slip small amounts, and that gives us earthquakes. Those faults can be made to slip if we change the stress state around them, and it's pretty easy to do that. These faults exist in rock that has fluids in the rock, and those fluids have a pressure, a pore pressure to them, like pressure in a bicycle tire. And if you increase that pressure near a sensitive part of a fault, and other conditions are also satisfied, you can cause that fault to slip and make an earthquake. And one way to do that is to inject fluid back into the subsurface and increase the pore pressure in the rock near the fault and destabilize the fault. One way is by hydraulic fracturing. The process of extracting oil from unconventional reservoirs, which is so prevalent now across Texas, especially in West Texas, involves drilling wells down into the ground and then turning those wells and drilling them horizontally. And they can go a couple of miles horizontally through the rock. Then, to make the rock deliver the oil to that well, the well is called fractured, hydraulically fractured. And from the surface, the way that's done is water and sand and some other things are pumped down the well at high pressure that causes the rock in that horizontal part of the well to break in regular intervals, they call them stages, and fracture the rock. And then those fractures will extend away from the well into the rock. And if it's all done right, which is pretty straightforward these days, then the oil flows back to the surface. But with that oil comes a lot of water. So I'll get to that water part in a minute. In rare occasions, that hydraulic fracturing itself can interact with these existing faults. And since that hydraulic fracturing is a pressurization process, it can cause a fault to destabilize and make an earthquake. So we've seen these horizontal well hydraulic fracture related earthquakes in some places in Texas, such as south of San Antonio in what's known as the Eagleford Shale play that the industry aggressively pursued in the last 10 years or so, and also a few areas of West Texas. But that cause is a much rarer cause of human-induced earthquakes in these petroleum regions, what's much more prevalent is that water that comes back with the oil as the oil is produced has to be disposed of. And the common practice for disposing of that water is to inject it back underground in other wells to dispose of that water permanently in subsurface formations. It's that process that is very widespread. Thousands of wells across the state of Texas do this every day, that then in some places can cause increase in the pressure and faults to slip. And I guess the last thing to note on that is in the Permian Basin, every day the petroleum industry has to handle 15 million barrels of this wastewater, and most of that is injected back underground.
Is that something that, is there any other workaround with that, or is that just the only way really to move that water when you're producing the oil?
Well, there are workarounds, and the regulator and industry have been working hard to achieve better performance with those workarounds. One of those workarounds is called recycling, where that produced water is then used as the source water for future hydraulic fracturing operations. And so that water gets used again and again, because after you fracture one of these wells, the water you use to fracturing it flows back to the surface also, along with the water that's already in the oil reservoir. So recycling helps, but it seems like that recycling process has reached kind of a plateau where it can't take any more of the water for the fracturing requirement. So there's a lot of water that needs to be permanently disposed. There are pilots underway in the Permian Basin region to filter and treat this produced water for what's called beneficial reuse. Maybe this beneficial reuse could be used for crop irrigation, to assist with livestock production, even to recharge natural drainages in surface water flows. But we're a long time away from that, because this process of filtration and treatment is expensive and it's slow, and it doesn't now handle the kind of volumes that could offset this huge volume of water that's produced every day. So the practice for now and for the years ahead anyway is going to rely on this subsurface injection, and then in some places we're seeing these injection-induced earthquakes.
So we've had a lot of news about this. Is there a trend that we're seeing of more of these induced earthquakes happening across the state of Texas over the last few years or decade?
Well, there certainly has been an increase in the last decade in Texas as the unconventional development of shale basins became prevalent, beginning in the Dallas-Fort Worth area and the Fort Worth Basin around 2008 and 2010. There were injection-induced earthquakes there, but those earthquakes ended once the rates of this injection and disposal went down as that petroleum system reached its ultimate life. Then the activity of an increase in earthquakes shifted out to the Permian Basin region as that region economically started to develop all of its unconventional resources. So beginning in 2017 and 2018, we saw the rates of these earthquakes increase out in the Permian Basin as well. And those rates increased to a maximum in 2021. And what we've seen is the monthly rate of those earthquakes was the highest then, and it has come down since then from that peak. But there are pockets or clusters, we call them, of earthquakes that occur or kind of pop up in unexpected areas, like the one last week, where the rates just get higher in a localized area. But it seems pretty straightforward that the process of injection is the most likely cause. And as this injection moves out in other areas of the Permian Basin, such as happened for this cluster that we recorded last week, we will see new areas of earthquakes from time to time.
So one thing I really thought was interesting with your work with the Bureau of Economic Geology is kind of the partnership that y'all have with not only the public sector and the research side, but working with these petroleum companies. How does that help to learn more and potentially help stop this activity?
Yeah, appreciate that question. Our center is funded by a variety of sources, and one of the sources is by sponsorship of the petroleum industry. And we have 30 industry sponsors who provide us funding on a yearly basis, and they look to us to do research that helps understand the specific causes of these human related earthquakes, these induced earthquakes. So that helps to fund our program, and also a number of our sponsors provide us with data and advice to help us dig deeper into areas where we would be unable to, on the public sector, do that ourselves. And so the Center for Injection and Seismicity Research is collaborative between the researchers in the center, the industry, and the regulator, because we're also funded by the Railroad Commission of Texas, the New Mexico oil and gas regulator, and also at the national level. I mean, everybody is pulling on the same end of the rope here, trying to understand what the causes are so that these practices can be made more sustainable. In a given area, if injection causes a lot of earthquakes, the Railroad Commission then requires these injection well operators to suspend their activities, which is an economic loss, investment loss, and it's just not what anybody wants. So what the industry wants and what the regulator wants is that the industry is as sustainable as possible, and the creation of induced earthquakes is not a sustainable thing. And so this collaborative that sponsors our research has these aims to understand where and when the earthquakes are most likely to occur, so that the industry activities can be as sustainable as possible and mitigate the chance of causing those earthquakes down, which has happened successfully in many cases thus far in the Permian Basin region. Those areas that were the most active in 2021 have seen a dramatic decrease in the rates of earthquakes in the last couple of years. Far West Texas, northwest of Pecos, for example, problematic earthquake clusters very close to Midland and Odessa. Those problematic areas have experienced far fewer induced earthquakes in the last couple of years as compared to those peaks. And that is the result of this collaboration of research, data, the regulator, and the industry kind of all working together to understand what's going on and put more sustainable practices in place.
So you're talking about kind of learning where they're happening and get ahead of it. How much does it help having the TexNet mapping ability now that you're getting observations all over the state and maybe catching some of those small ones to learn about before the big one happens?
Yeah, well, having the TexNet earthquake catalog is probably the most important aspect of all of this. That's the state-funded seismic network that's operated out of the Bureau of Economic Geology, and that earthquake data is the enabling thing that helps us understand where the earthquakes are happening, how those trends are changing over time, and that data gives researchers and the industry and the regulator some proactive ability to see how things are changing over time and space to try to get ahead of it and to do a more thorough job of mitigating the earthquakes where we know they exist. That data is absolutely essential.
Well, Dr. Hennings, I appreciate you taking some time to talk with us and shine a light on this. I'm very interested to learn kind of the science side of this, but thank you for talking with us today.
Thank you, Brady. I appreciate it.